that I'm audible?
Yes, sir.
Okay, thanks. Right, so far we've seen three different uh, prefix-free variable length codes: the Shannon code, the Shannon-Fano-Elias code, and the Huffman code. We've seen that the Shannon code achieves an expected length, which is between the entropy of the source and entropy plus 1 bits. The Shannon-Fano-Elias code is worse than that. It achieves something between h of x and h of x plus 2 bits. And the Huffman code achieves an expected length, which is also between h of x and h of x plus 1 bits. But we've seen the optimality of the Huffman code, and that is that among all possible prefix-free codes, the Huffman code achieves the minimum possible expected length. So this is what I denote by L star of px. So among all variable length prefix-free codes, uh, L star of px is the minimum possible expected length, and the Huffman code achieves this expected length. And once again, I'd like to remind you that the code which achieves the minimum expected length is not necessarily unique. There could be multiple codes which achieve the same, which achieve L star of px, but you can't do any better than this. You cannot achieve any expected length which is less than that achieved by the Huffman code. So before we proceed, are there any questions? Any questions? All right. So uh, one question that was raised in an earlier class when we were discussing the Shannon-Fallow-Elias code was that why do we even need this? So we know that the Huffman code is optimal; it achieves the minimum expected length. Then why do we need a separate Shannon-Fallow-Elias code? And we'll see the reason for that today. But even before we go to that, there's one important point that we need to discuss. So what is the complexity of constructing a Huffman code? So at least in terms of the order, what is the number of operations required to construct a Huffman code? So recall that, so how do we construct the Huffman code? So we do it in steps. So first, find the minimum, or find two symbols with the least probability. Probability and then merge them, right? And do this, right? Keep doing this till you have only one symbol left. Right? So can someone tell me, at least roughly, what is the complexity? I don't want the exact number of operations, but if I want to construct a Huffman code on say m alphabets, so if the alphabet size is m, then how many operations would be required to construct the Huffman code for this? So log m. So why do you say log m? What do you mean divide by 2 each time? Right, so it's roughly m log m, right? It's order m log m, because first you need to find the minimum, uh, the two symbols with the least probability, and overall this will take like order log m operations, and but then you need to do this at each step, right? And at each step, the number of steps that you have to do this for is m, right? Or whatever, m minus 1 steps, right? So the overall complexity is order m log m, right? So to construct, well, it's at least omega m, right? Where m is the alphabet size, m is the number of symbols over which you want to construct a Huffman code. Okay, and what have we seen? We've seen that the expected length achieved is between h of x and h of x plus 1 bits. So in the worst case, for the worst uh, possible uh, distribution, the expected length that the Huffman code achieves is h of x plus 1 bits. Right? So for a general uh, distribution, let us suppose that we have some distribution px, okay, where the expected length achieved by the Huffman code. So it's a distribution on, say, m symbols, on whatever. It's a distribution on some alphabet px on some alphabet calligraphic x, and the expected length achieved by this, let us say, is h of x plus alpha bits. Okay, where alpha is something between, which is strictly greater than 0, but it could be less than or equal to 1. Doesn't matter what alpha is exactly equal to, but alpha depends on px. Okay, so this is the expected length achieved by the Huffman code for this particular distribution. Right, so maybe the distribution is something like 0.3, 0.2, 0.1, and whatever, 0.4. Let's say. Okay, some distribution, and this is the expected length that is achieved by the Huffman code. Okay, so this is all fine if we want to encode only one symbol, right? But typically this is not, in a practical application, this is not what we're doing. We have a large file which consists of n symbols, right? x1, x2, x3, x4 up to xn. This is the actual source. And what we could do is we could do symbol wise compression of this. So you compress each symbol using the Huffman code design. So maybe each xi comes from A, B, C, D, and the probabilities are as we have over here. Right? So we encode each symbol separately, and then we concatenate this. Right? So we design the Huffman code for px, and then we do symbol-wise encoding of all the n symbols, and then concatenate this. So, and we know that the expectation of k of x is h of x plus alpha bits. So what is the expected length for encoding xn? What is this equal to? Yeah, so this is n times that, right? So it is n times h of x plus alpha bits, right? So if we compare, but what is the entropy of xn equal to? If it's an IID source, if it's a memoryless source, yes, anyone? What is h of xn equal to if xn is IID? It's n times h of x, right? So the entropy is n times h of x, but the expected length achieved by this is n h of x plus n times alpha for some constant alpha greater than 0, right? So the difference between the expected length and h of xn, which is really the limit of what we can achieve, so this is equal to n alpha bits. So as n grows larger and larger, this gap to entropy keeps growing, right? So this grows linearly with n. This is proportional to n, right? And that's pretty bad, because the larger the size of the file is, the farther away you are from, you're going from the entropy of the total entropy of the source. But this is if you do symbol-wise encoding. Now, what can I do? I can design a Huffman code for xn separately, right? So the first solution that we can think of is don't do symbol-wise encoding. You instead design a Huffman code for xn. Or whatever xn. Right? So if we design the Huffman code for xn, then the expected length that we can now achieve is somewhere between h of xn and h of xn plus 1 bits, right? And so that is great. So it's h of xn plus 1 bits. So we're almost close to the entropy, right? So it's a gap of almost 1 bit away from entropy, and this is fine. Right? So the larger n is, the closer you get to h of xn. So the rate, in fact, tends to h of xn by n. So this is great, but then what about the complexity? So what is the complexity of constructing a Huffman code for xn? Yes? Anyone?
Order of n log n?
It's not order n log n, right? So it is, if the alphabet size is m, right? So if the alphabet size, if the number of symbols is m, then the complexity is order m log m. But here, what is the number of symbols? If I want to encode xn, right? So the complexity, as Ritwik mentions, is the alphabet size is now size of x to the n. So it's cardinality of x to the n. So the complexity will be cardinality of x to the n log cardinality of x to the n. Right? So it grows. So the complexity grows exponentially with n. Right? And clearly, this is not acceptable. This is not a practical algorithm for large enough size. So so for example, if we want to encode an ASCII text file, right? So the cardinality of x would be say 256, or let's say even if we want to encode say English, so sequence of English characters. So let's assume that all we have are the 26 letters in the English alphabet along with spaces. Okay, it's a gross simplification. So 27 symbols, and I want to encode, say, a text file which is of size say, even 1 kilobyte, right? 1 kilobyte. So the complexity of constructing the Huffman code would be at least 27 to the raised to 1000, which is a humongously large number, right? So it's impossible to construct a Huffman code for such a large alphabet, right? So what do we do? So therefore we need a better algorithm which gets you at least close to h of xn. So maybe h of xn plus 1 is too much to hope for, but can we even get to within a constant of h of xn, but at the same time have a code construction complexity which is small enough, right? And that is really the goal of of what we want to do next, and we'll see how to do that using the ideas that we see about Shannon Fano LIS code, right? So so just to quickly recap what we've done just now, we've seen that if we do symbol wise so we've seen that so Huffman codes are optimal, they achieve the minimum expected length, and if we do symbol-wise encoding, then the expected length that is achieved by Huffman code is n times h of x plus some constant times n. So the gap to entropy, the difference between the expected length and the entropy of xn grows linearly with n, right? But if we want to get uh, a smaller redundancy, then what we can do is we can do blockwise encoding instead of symbol-wise encoding. But unfortunately, the complexity uh, of constructing the Huffman code grows exponentially in the size of the block. Right? So you can achieve an expected length which is within a constant of the entropy, but the complexity grows exponentially in the size of the block. So we want to construct a code which achieves an expected length within a constant gap of entropy, but at the same time has linear or at most quadratic complexity in the block size. Okay, any questions? Right. So any questions so far? Yes, any questions? So this brings us to what is called arithmetic codes, which is just sort of an extension of Shannon-Fano-Elias coding. Okay, so let's see what we did in Shannon-Fano-Elias coding. So there we first computed f bar of, so for each symbol, or in other words, if we wanted to encode x, say suppose we want to encode xn, then what do we need to do? We need to compute f bar of xn. So it's the sum overall an less than xn. So whatever this means, I'm being a little loose here when I'm saying an less than xn. I haven't clearly defined what that means. P of an plus p of xn divided by 2. So we need to compute f bar of xn and then look at the binary representation. And then truncate, or basically get the first seal log 1 over p of xn plus 1 bits. Right? So the basic idea behind the arithmetic code is that unlike the Huffman code, in Huffman codes, if we want to construct, or if we want to obtain the Huffman code word for xn, then the only way we can do this is by constructing the entire Huffman tree. But the idea behind the Huffman code, behind arithmetic codes, is that you don't construct the entire code word tree. You somehow try to construct only the code word, or the code word for only the symbol that you're interested in, that is xn. So you're given xn, and you try to construct the code word for xn without constructing the code words for other symbols, which you're anyway not interested in. Right? And it turns out that so arithmetic codes are essentially Shannon-Fano-Elias code done a little cleverly, right? So what is the basic idea? So we're given, so without loss of generality, we will assume that the alphabet is the set 0, 1, 2 up to m minus 1. Okay, suppose that the alphabet has m symbols, then we can always, I mean, in any arbitrary fashion we want, we just map these symbols to to the set of first m minus 1 non-negative numbers. So we'll assume that the alphabet is 0, 1, 2 up to m minus 1. So for example, if you want to encode, say, English letters, then this would be 0, 1, 2 up to 25. Okay, so this is going to be our alphabet, and a key idea is that you can represent any string xn in Emery form, and you can map this to a number which is between 0 and 1. Okay, so what do I mean by this? So let's take an example. Suppose I have say m equal to let's say 4. Okay, so the alphabet is 0, 1, 2, 3. Okay, and if I have a sequence, if I'm given a sequence xn, say 0, 2, 1, 1, 3, 1, 0, then I can represent this in the quaternary form as 0.0211310. Right? This is in quaternary. Right? So, and this is a number between 0.x1, x2 up to xn. So this is going to be between 0 and 1. Right? So in fact, this is strictly less than 1. Okay. So any questions so far? So basically, the idea is that given a sequence of length n, I'm going to map it to a real number in the interval between 0 and 1. And the way I'm going to map this sequence to a real number is just by taking 0.x1, x2, x3 up to xn in the Emery format. And this corresponds to some real number, 0.a1, a2, a3, and so on, in the decimal format. Right? Any questions? Oops. Okay. So let us suppose that the alphabet is in fact binary. Okay. So without loss of generality, we're assuming that the alphabet is Emery, and basically as a real number, this can be represented as 0.x1, x2, x3 up to xn, and the real number that this corresponds to is essentially summation I going from 1 through n xi divided by m raised to I. Right? So that is what the real number that this corresponds to. And to understand this better, it's useful to look to think about the CDF. Right? So the CDF is basically looks like this. So for n equal to 1, let us assume that m equal to 2. So we have two symbols in the alphabet, and the length of the sequence is 1. So we just have one bit, and the CDF corresponding to this would be this function that I have over here. And what would you do if you had to construct the Shannon-Fano alias code? You would just take so the midpoint of this particular interval over here, and then so I would just take the midpoint over here and then represent this number 0.6 in binary format, truncating it to whatever p of x bits. Right? Similarly, if I wanted to encode bit symbol 0, then I would first compute f bar of xn, which is the midpoint of the midpoint over here, and then construct and then truncate it to log 1 over p of x plus 1 bits. Right? So now what if we have two symbols? So if I have two symbols, then this is what the CDF would look like. And once again, if you had to construct the Shannon-Fano alias code, then you would take the midpoint of the symbol that you're interested in. So this particular interval, take the midpoint. This corresponds to some real number, and and you just take the binary representation and truncate it to log 1 over p of x plus 1 bits. Right? So as you keep increasing the sequence length, as you go from n equal to 1 to n equal to 2 to n equal to 3, the size of the interval keeps shrinking, but so it keeps shrinking and it becomes sort of smoother and smoother. Right? But one very important point to note is that ultimately what we're interested, so if we're interested in constructing the code word for one particular for say 110, then it's enough if we know p of xn, so p of 110 and this interval, right? So because we need to find out the midpoint of this interval and then look at the binary format of that. Right? So as long as we are able to compute this interval in an online fashion, so in a very low complexity fashion, we're good to go, right? Because the rest of it is not important. To construct the code word for the sequence 110, all we need to know or all we need to compute is this particular interval. And we'll see how to do this in an efficient fashion. All right. So, so to see why we can compute it efficiently, let's start from n equal to 1. So this is n equal to 1, and so corresponding to, so ultimately we're still interested in computing this interval for 110. Okay. So let us look at the first symbol. We get the first symbol. We know that it is a 1. So the interval is between whatever 0.25 and 1. Right? So we know that it's between 0.25 and 1. So the remainder is not really important to us. If you look at 1, 1, right, then the interval corresponds to this particular region over here. All right, it's this particular region, which is always a sub-interval of this interval. Right? It's a sub-interval of this particular interval. Now, if you look at 110, it's again a sub-interval of this interval over here. Right? So this is ultimately the region that we're interested in. Okay. So to compute the interval for 110, I can first compute the interval for 1, and then compute the interval for 1, 1, and then the interval for 110. So if I can do this in an efficient manner, then I'm done. I have this interval. I can compute p of 110 very easily because it's just computation of a probability, which is easy. And hopefully, as long as I can compute this interval, I can compute f bar of 110 and therefore construct the code. Right? And the basic mathematical idea can be captured by this recursion, which we'll see next. Right? But before we move, I mean, at a very high level, any questions regarding the basic idea behind this? Yes. So essentially what we'll be doing is to compute f bar of 110, we'll compute f bar of 1, then we'll compute f bar of 11, and then compute f bar of 110. So we don't really need to compute f bar for any of the other symbols. We'll have a recursive formula to compute f bar of xn. All right. So let's let me get back to my handwritten notes. Okay, so our goal, so the goal now, if you want to construct the Shannon-Fano alias code, so construct or compute f bar of xn and p of xn efficiently. All right, and how do we do that? So I'll define a new symbol, new function. Let me call g of xn, okay, or g of x, which is sort of like the CDF or the modified CDF, but it is summation over all a strictly less than x of p of a. Okay, so the CDF is basically summation over all a less than or equal to x of p of a. The f bar is summation over all a less than x of p of a plus p of x divided by 2, and g of x is just summation over all a less than x of p of a, right? So we have this. P of a, which is g of x plus p of x, and f bar of x is g of x plus p of x by 2. So if I can compute g of x efficiently and p of x efficiently, then I can compute f bar of x or f of x uh, very easily. Okay. So one reason why I did this, so note that I'm representing a particular sequence as I'm representing a particular sequence xn in the emery format. So I can think of this as 0.x1, x2, x3 up to xn. And sort of the reason why I use this emery format is twofold. So firstly, this imposes an ordering of the sequences. Right? So if I have two sequences, say 1, 2, 3, 1, 0, and 2, 1, 3, 2, 1, okay, I can say that the second is greater than or equal to the first because 0.12310 is less than 0.21321, right? So that is one reason. So this emery representation imposes an ordering. All right, so it makes sense to talk about g of xn, which is summation over all an less than xn of p of an. So this is well defined. Okay, and the second very interesting property is that Let us look at, say, 0.1 and 0.2. Okay. Uh, Now, if I observe the sequence 1, 3, right? So if I append anything after 0.1, I observe, say, 1, 3, 2, 1, 0. This is always greater than 0.1, but is always less than 0.2, right? So suppose I have a sequence xn, and I observe the symbols one after the other. 1, 3, 2, 1, 0, 2, 3, 3, so on, right? So this, no matter what the rest of the sequence is, this is always greater than or equal to 0.1 and is strictly less than 0.2, right? So so the rest of this sequence always lies in the interval between 0.1 and 0.2. So similarly, when I observe the second symbol, so 0.13, the rest of it is going to lie between 0.13 and is going to be strictly less than 0.14. Okay, so in this case, the alphabet is of size 2, so it's 0.20, right? And when I observe the next symbol, 0.132, I know that what is going to come after this will lie between 0.132 and 0.133, right? And we'll use this property. Okay. So in fact, we can show that so the goal now is to compute g of xn and p of xn. Okay, p of xn can anyway be computed very easily in a recursive fashion, because this is just p of xn minus 1 times p of xn. So that's a very easy recursion to compute. But in fact, we can compute g of xn very easily. So I claim that g of xn is equal to g of x n minus 1 plus p of xn minus 1 times g of x subscript n. All right. So any questions so far? So if we use this recursion, then basically if we assume that it takes unit time to compute each step of the recursion, then to compute g of xn, we just need to take n time which grows with n, right? So we still have just linear time. So g of xn can be computed in time order n, right? P of xn can also be computed in time order n. So even as n grows, the complexity of computing g of xn and p of xn is small. It is still growing linearly with n, and therefore you can compute f bar of xn, and of course you've already calculated p of xn. So you can do all of this in time which is still only linear in n. Okay. Any questions? Any questions? Okay, so maybe this is a good time to have a quiz. Uh, I put the link in the chat box. It can take maybe 4 minutes or so to solve this. Yeah, so you can let me know in case you haven't got the link. We can take maybe 1 more minute to submit your answers. Okay, so is there anyone who was yet to submit their quiz?
Yes, sir. Wait for a second, sir.
Sure. So, all done.
Yes, sir.
Okay, so I'll stop accepting responses. All right, so, let's see. Uh, so our goal is to show that g of xn equal to g of xn minus 1 plus p xn minus 1 g xn, right? And the basic idea is the following. So g xn is summation over all a n less than xn of p a n, right? And we're going to write this, split this into two parts. So the sum over all a n less than xn minus 1 0 and the sum over all a n which are greater than or equal to xn minus 1 0 but less than xn of p of a n. Okay, so right now I've just split this into two terms. Okay, so this I can write this as summation over all a n minus 1 less than xn minus 1 and a summation over all a n of p of a n plus. So in the second term, the first n minus 1 symbols is always xn minus 1, and it's only the nth symbol which varies. Right? So it is just a n less than xn of p of xn minus 1 p of a n. Okay, so I'm going to split the first term once again. A n minus 1 less than xn minus 1, and p of a n can be split as p of a n minus 1 times p of a n. All right, so this is this plus p of xn minus 1 times summation a n less than xn of p of a n. Right? So what is the first term? This is just f of xn minus 1. What is the second term equal to? Yes? Is equal to 1 plus p xn minus 1. And what is this term equal to? So the summation over all a subscript n less than x subscript n of p a subscript n. Yeah, so it's just, yeah, exactly. So, oh, sorry. So this should be g xn minus 1 times g of xn. So it's f of xn minus 1, or it's just g of xn, right? So we have g of x superscript n equal to g of x superscript n minus 1 plus px superscript n minus 1 g x subscript n. Right? So now we have a nice recursive formula to compute g, and once you compute g, we can compute f bar of xn, and therefore compute the code word. Right? And we can do this without constructing the entire code word tree. Right? So any questions? All right. So if there are no questions, then we'll end the meeting for today.